the thing about numbers that's weird is that when we read from left to right. Even when you read numbers, you read left to right when you actually pronounce a number. The problem is that numbers really go from right to left in terms of the significance of each of the digits that make up a number, right? And these kind of, this comes up a lot also in HDL design. Now, just to sort of clarify this, if you take a base 10 number like 5,374, like I said, you read it from left to right. But if you're trying to figure out what value this represents, you've got to go from right to left because that 4 has the least amount of significance. It carries a significance of the base to the 0th power. So 10 to the 0th power, and then the next digit working your way from left to right is the 7 that has a significance of 1. So it's 10 to the 1st, that's the tens position. Likewise, 3 is the 100s position, right? So, normally you see a number, you would have to, especially if it's a really big number, right? You can't really, like if you have a really long number, you can't really read it from, it's hard to read it from left to right. You got to go from right to left, right? Binary works the same way, except the base is 2. So if I have a number like 1101, this rightmost bit, just always start from the right, carries a significance of 2 to the 0th power, which is 1. So that gives me 1. That gives me nothing, because there's a 0 there. This gives me 4, 2 to the 2nd power, and then this gives me 8, 2 to the 3rd power, right? You guys remember that from 211? Now, at some point, you should be able to just look at that binary number and know immediately, because if you see enough of these 4-bit numbers, because each one of these 4-bit numbers is usually grouped to a hex number, right? So that's 13. I could just tell from looking at it just because I've been looking at these for so many years. So if I asked you to convert a number to decimal, a binary number to decimal, you can just, the easiest way to do it is to look at each bit from right to left and just add up the power of 2 that bit represents. And so you would add up all the ones that have a 1 position, right? Has a 1 in that position, right? Going from decimal to binary is a little harder to do that. I do it, this is not the way the book does it. I do it differently than the way the book didn't really have a really good method to do it, actually. But the way I always did it was I took the number and I keep dividing it by 2. And every time I divide it by 2, I give the remainder, right? So if I have 47, you take 47, you divide it by 2, and you get 23 with a remainder of 1, right? And then 23 divided by 2 is 11 with a remainder of 1. 11 divided by 2 is 5 with a remainder of 1. 5 divided by 2 is 2 with a remainder of 1. 5 divided by 2 is 2, remainder 1. 2 divided by 2 is 1 with a remainder of 0, right? And then you read the numbers from the bottom up. So you go, including that the last number in this column will always be a 1. So you go 1, 0, 1, 1, 1, 1. Make sense? I think that's the way I always did it. Did you guys do that in 211? No? Okay. I think that's an easy way to do it. Now, normally when I write it out, I put the remainder actually on this line. So I'll put 47 and 23, and I'll put the 1 over here. But I couldn't find a good way to do that with the table there. OK, how about if I have an n-digit decimal number? Notice it's n-digit, n-bit. Digit is for base 10, bit is for base 2. But they represent the same thing. It's like a position inside the number, right? Likewise, it gets really weird with decimal point, because binary numbers can also have fractional components, which I'll cover here in a little bit. You can have a fractional binary number. I don't think you guys covered that, I don't think you covered that in 211. But you can have a binary number that's like 11.01, for instance. You can do that. But that point, what do you call that? We always call that decimal point, but it's not a decimal number. It's a binary number. What do you call that thing? I think I always called it a radix point. I think is the kind of the general term for a dot that differentiates the whole and the fractional part of a number is the radix point. But I always still screw up and call it decimal point, even when I'm doing binary numbers. Anyway, n-bit decimal number, how many values? You guys remember that? How many unique values? Well, it'd be the base to the n, right? So in this case, this one's decimal, so it would be 10 to the nth power, right? Right? 10 to the nth power, right. I'm going to cheat and put the answers up. Range, 0 to 10 to the nth minus 1, right? So if it's a 2-bit, 2-digit number, it's 0 to 99. Right? Make sense? OK, binary would be 2 to the n. The range would be 0 to 2 to the n minus 1. OK, this is assuming that this is an unsigned number. So for a 3-bit number, it's 8 possible values, 0 to 7, right? You guys with me on that? This coming back? It should be coming back to you. OK, hex numbers are just shorthand for binary. So you take 4 binary numbers, you group them together, and you get a hex number. Hex numbers are base 16, so they're 0 to F. 0 to 9, and then A through F. Now, that's kind of weird. Musical notes go from A to G. Music notes, A to G. This is A to F. So we have to remember this now. A to G if it's music. A to F if it's hexadecimal. Yeah, there's an A to G note. That's confusing. So hex digit 0 to F. Decimal equivalent is 1 to 15. And then there's a binary equivalent. Binary equivalent. So C, what is C? 1100, it's 12. What's F? 1111. Right? Make sense? You guys, I'm sure, have noticed that binary numbers are never shown in binary. Never. They're always shown in hex. So every time you have a crash on your computer, it's always shown, you got a bunch of hex numbers come up, because binaries are just too long. The binary number is too long. So if we use hex, we basically compress. The thing that stinks about hex numbers is that there are very few English words that only contain the letters A through F. Dead beef is one, decaf bad, and bad dad. And that's it. That's literally the only English words you can form through A to F. It sucks when you're trying to come up with test data to put in. I like decaf bad, though. That's a good one if you like coffee. So hex. How do you convert hex? These are all questions I'll ask you on the quiz. So make sure you can do this stuff. How do you convert a hex to binary? Oh, it's easy. 4 is you kind of have to memorize it, I guess. What is 4? 4 is 0, 1, 0, 0, right? A is 10. Oh, I always think, the way I think of it is like I see A and I think, okay, A is 10. And 10 is 1, 0, 1, 0 in binary. Because you have to take 1, 0, then you got to put the 8 and the 2 is 1, 0, 1, 0, right? The 8-bit is on and the 2-bit is on, right? F is 1, 1, 1, 1. And then hexadecimal to decimal conversion, I think the book actually, I think the book actually suggests that you convert it to binary first, but this is much simpler. You just do the same thing you normally would do with any number in any base, but just use 16, right? But it's kind of weird here, though, because this is F, and that's A. So how do I type A times 16 to the first power? No, you don't do that. You do 10. Oh, 16 times 10. So you have to kind of, this technique requires you to do 2 conversions, really, because you got to do 1 conversion, at least for the A to F, right? Because you can't multiply 16 times to the first power times A. You can't do that. That doesn't make any sense. So you have to convert the A to 10. That's 1 conversion. And then you got to multiply these things up and add them up, right? Does that make sense? So that's... Any questions about that? Hopefully I didn't. I'm going kind of fast because I'm assuming you guys have seen this stuff before. Okay. Now you might say, wait a second, let me ask a question here. how much of this stuff is, I mean, you're talking about doing HDL design and building up floating point units and stuff. How much of this number conversion are you doing when you're doing that stuff? Turns out you'd be surprised quite a bit. You have to do a lot of addressing calculations whenever you make a RAM, and there's a lot of bit twiddling. It's actually called bit twiddling, that's a term, bit twiddling, where you're taking bits and combining them together and stripping bits out, and a lot of that kind of stuff. So you have to sort of have this sort of stuff, you know, sort of second nature, as strange as it may seem. This stuff should be like, you know, you should be able to do this in your sleep. But it's, you know, like anything else, if you're not used to it, it takes practice. Okay, a couple other terminology things. I think you guys know what a bit is. However, the most significant bit is the left, and the least significant bit is the right bit if you have multiple bits. Now here's where things get wacky. It's the third to the most significant bit. I get a lot of that. Like, I don't know how to describe. It's the second least significant. It's the fourth least significant bit. What does that mean? We'll start with the least significant bit and go 4. It's the fourth one. Or you could say it's the second most significant bit, which would be the one right next to the most significant bit, going to the left. That makes sense? So you might hear that kind of stuff. Because this way you only get, you're only most significant and least significant, and it only gives you access to 2 bits. Byte is 8 bits. Sometimes if you're pretentious, you call it an octet. I call it a byte. Octet is French. No, it's a byte. Bytes kind of like pennies these days. Kind of useless. Everything is so big. Everything's 64-bit words. Pixels are 24-bit, even RGB pixels. Nothing's a byte anymore. Even characters. No one uses ASCII anymore. They use Unicode, which can be more than 8 bits, multiple bytes. Instructions are multiple bytes. Nothing is a single byte, hardly ever anymore. Byte is almost a completely outdated, useless term. But the problem is, though, is that we have to stick with it. Because the minute you start changing what a byte is, things will really fall apart. Because all computer addresses are byte addressed, even though they have to actually be word addressed, because if the byte address is not divisible by 4, you'll segfault. So it's kind of like, well, if it's always, that means the lower 2 significant bits are always 0, isn't that kind of waste? Yeah, but we have to keep everything consistent, so we're going to stick with the byte, right? Even though it's a really tiny amount of data. Likewise, Nibble, which you don't hear as often, is 4 bits. If you say most significant byte, that's the leftmost byte, least significant byte, rightmost byte, right? Now, this gets kind of weird because sometimes we have different byte orderings where you have to rearrange the bytes. But the way this is written, that's the most is left, least is. This, by the way, refers to this least and most significant. You know, normally we think of it as left and right, but it really refers to the significance, you know, about what value those things carry. All right, anyway. Okay, this is the part that's crazy. This really, I never can get used to this. So 2 to the 10th power is 1,024, which is kind of a weird number, right? What's the significance of 1024? Well, the significance is it's almost 1,000. And we have an SI prefix for that, kilo. Except here's the problem. If you're using prefixes, scientific prefixes, you have to be precise. So which is it? Is it 1,000 or is it 1024? A kilobyte cannot be 1,024 bytes because a kiloton is 1,000 tons. So for years, this confusion just ran rampant for decades and decades until, I don't know when it was, it seems like it was recently, somebody decided that we're no longer going to have kilobytes. They're gone. We're going to have kibibytes. I swear, this is real. A kibibyte is 1,024 bytes, which I used to always call a kilobyte, but that's not a kilobyte. A kibibyte is 1024, and it is written K, uppercase K, lowercase I, uppercase B. It's not a kilo, it's a kibibyte. There's a mebibyte, which is 2 to the 20th power, which is 1,048,576 bytes, which this number, after 30 years, I can never remember that number. I couldn't give you that number from memory. So I always open up Windows Calculator and type 1024 times 1024 to get that number. So it's a 1024 kibibytes, or 2 to the 20th bytes, which is almost a megabyte, but never say megabyte. Likewise, gibibyte. A gibibyte is 2 to the 30th bytes, and it's just over 1 billion bytes. But it's technically it's 1,073,741,824. That's 1 gibibyte, 1 GIB. So the question is, if 1 gigabyte is 10 to the 9th bytes, who would ever use gigabyte again? In what unit would we ever use a gigabyte? What context would we ever use a gigabyte? Well, some people say, well, hard drives are actually, if you have a 10 gigabyte or 1,000 gigabyte hard drive, it's actually 1,000 gigabytes. Giga, not gibby. But every other thing is measured in gibibytes, right? Anyway, make sense? Okay, so this is some shortcuts. What is the power of 2 to the 24th power? The idea is, if you know that 2 to the 20th is a mebibyte, then you can kind of break this number out, because 2 to the 24th is 2 to the 20th times 2 to the 4th. So 2 to the 4th is 16. So this is 16 mebibytes. Well, if it was 2 to the 24th bytes, it would be 16 mebibytes, or roughly 16 million different values, right? This is significant because a lot of times video data is stored as a 24-bit pixel, because you've got 8 bits of red, 8 bits of blue, 8 bits of green. Sorry, red, green, and blue. I had it in the wrong order. And so everyone used to say back in the 90s, video cards would be marketed as having 16 million colors. Well, that was just because they were using 24-bit, pixels, and that's where that came from. How many values can a 32-bit? Well, 32-bit, if 2 to the 30th is your gibby bytes. So gibby is about 1 billion, and 2 to the second is 4, so 4 billion. So you kind of have to break those down that way. Otherwise, you think 2 to the 32, it's like, what is that? Okay. So basic addition, I think everyone's known this since like first grade, but you add numbers up. This is the part though this part actually gets a little weird, because notice that you add numbers and you have carries, right? Everyone remembers that. But the significant thing, one thing you might not realize is that when you add numbers up like this, you're lining them up in a certain way. And the lining them up actually has to do with the significance of the numbers. And so because there's a hidden radix point or decimal point here, we have to line up the decimal point. This will become important once we get into fixed point numbers. When we start adding fractional binary numbers, you have to make sure that they're lined up before you add them, right? Binary, you add the same way, except the carries can can only be 1 when you carry from one digit to the next, right? You guys remember that? Okay. Here's a couple examples. Now, you guys probably learned in 211 that these carries are a pretty simple idea. Everyone learns this stuff in elementary school. But it turns out this is a major headache when you try to design fast arithmetic on a computer, because the carries create a dependency chain in which you have this critical logical path that has to go through all of these carries that makes adding very slow in binary. This is one of the things that actually limits computer performance. How fast can you make an adder? Well, you got to the more the bits that you want to add up, the longer of a delay you have to generate all the carries. And so and of course, like I said when I was talking about abstraction, remember adders form the basis of multipliers, and multipliers form the basis of more complex things. But ultimately, it all comes down to adders, right? So if you can make your adders faster, you make everything faster, including dividers, believe it or not. So, but these carries, you know, we'll talk more about that later. Okay, let's see. It's just after 5. Let's see. I'll cover this and then we'll break, I think. Yeah. Okay. So let's talk about 2's complement as the last topic, just to review this. Again, I know you guys have covered this, but we just want to make sure everyone's on the same page here. You guys did cover 2's complement, right? Okay. So 2's complement is a way to make binary numbers have a sign, right? Not just be a 0 or positive number. I guess at one point, I don't know if this was ever a thing. I think at one point someone used something called sign magnitude, which is where you basically just set the first bit as the sign bit, right? And then the rest of the number was just normal, right? Seems straightforward, except it doesn't work with adders. If you want to add 2 numbers with that adder I just showed you, and one of the numbers is negative, you can't use, if you try to use sign magnitude, the math doesn't work out. You won't get the right answer. So 2's complement is, I remember when I first learned it, I thought it was kind of, I thought that they were doing it just to torture us, because it seemed unnecessarily complex. But the idea behind 2's complement is that instead of the first bit being a sign bit, which is the most significant bit, the leftmost bit, in this case it's the first bit has a significance of n minus 1, right? You basically make that first bit be negative. So you give it the same significance it normally would have. So if it's a 3-bit number, the first bit has a weight of a significance of a 2 to the third 8, right? We just say, oh, it's -8. And all the other bits, no change. Just the first bit. The first bit has a significance of -2 to the n minus 1th power, where n is the total number of bits. So again, if it's a 4-bit number, the first bit would carry a significance of not 8, but of -8. And then you can treat all the other bits normally at that point. That's what this part is. This summation is just saying, convert all the other bits like we did in those first slides, right? So this way, this is a 7, and this number is -8 because it's basically -8 plus 0, because the other bits are 0, right? On the other hand, I thought I had more examples than that. I guess not. Okay. So the range then would be, in this case, 4 bits would be -8, right, is the most negative number, the highest magnitude negative number, right? But if you put any other bits to 1, you're going to be bringing it up towards the positive side. You get me? So the most negative you can go is -8. Any other bits you set are going to bring it towards the light. Right? So the range would be -8 to +7, right? Because +7 would be, don't set the big -8 bit, set all the other bits to 1, in which case we get 7. That's our biggest positive number. Right? So that's how 2's complement works. It's pretty simple. The other thing you probably learned was, if you want to flip the sign of if a number, you already have a number, whether it be negative or positive, and you want to flip the sign, you don't just flip the sign bit. That's no good. That'll screw things up. You have to flip all the bits and then add 1 to the result, which, I always thought, hey, that's overly complex. But it's the only way to make negative numbers work out mathematically. So you flip, let's see, if you have 1100. Now here's the other problem with 2's complement, by the way. If I have 1100, that's a 4-bit 2's complement number. Say someone tells you that, and they're like, what's the number? I don't know. I mean, if it's not, I can tell you that's C or 12 just by looking at it, if it's not a 2's complement number. Easy. 8 plus 4, 8, 4, right? Done. Someone says, what is it in 2's complement? I would say, well, the first bit is 1, so I know it's negative, but that's all I can tell you. I really don't. I don't. Give me a piece of paper. I'll figure it out. I don't know. I can't tell. Can't tell from looking at it. the way you figure it out is you have to flip all the bits, so it would be 0, 0, 1, 1, which is 3, and then you add 1 to get 4. So this is actually negative 4. 1, 1, 0, 0 is negative 4. See, that I don't have memorized. I couldn't tell you that. I'd have to flip the bits and add 1. Even for a 4-bit number, I got to do that. Actually, in this, I didn't follow the example right. So this is 3 in this case. You start with positive 3. So if you started with this, if you started with that as your negative number, that's negative 4. But in this example, you start with 3. Then you start with 3. You want to get negative 3. So you take that number. You get the 1, 1, 0, 0, which as I just said, it's negative 4. But then you add 1 to get negative 3. You guys with me? So again, that's kind of confusing. It's like if you have a number that appears to be negative because the first bit is set, take the 2's complement, get the positive form of it, and then just assume that the original version was negative, the negative version of it, right? So again, that was this was positive to negative, and then obviously if I had this and I wanted to go the other way, I would go 0, 0, 1, 0, which is 2. Add 1, I get 3. Okay. All right, so that's all I got for today. Thank you, and I'll see you on Wednesday.